And number 22, what we're going to do is figure out the rate law and the K value using data, okay, using the initial rate method. So the reaction that we're dealing with here, turn my page here, is, now when we use the initial rate method, we cannot just look at the exponents. Okay, it's a little misleading when I start off that way, but the reason that we could do that is because we were just simply looking at production and not necessarily exact experimentally determined orders of reaction. So that was just to kind of get us to the idea of determining what's going to dictate in terms of slowing things down or making things go faster. Okay, this is the reaction that we've got. It was studied at 25 degrees Celsius. The following results were obtained where, okay, we've got our rate, and they give us several different reactions where they change the concentration and then they give us the initial rate. And we need to figure out, two things. First, we have to determine the rate law. And so what we're looking for when we determine the rate law, remember that the general, we're going to have rate is equal to K. What we're looking for here is what is X and what is Y based on that data. So the first thing is we're going to find the rate law. Once we determine the rate law, we're going to go back, plug these numbers in, and solve for the K value. Okay, we're going to solve for the K value. All right, so how do we do that? Well, for the first one, let's do a green pen. For the first one, for my iodide ion, excuse me, I'm going to pick, what I'm looking for is two experiments where iodide changes, but the other one stays the same. So I'm going to go ahead and pick experiment number 1 and experiment number 2. And again, it doesn't necessarily matter which one you put on top. It depends if you want whole numbers or not. I'll put number 1 on the top. So for iodide, to solve for X, I'm going to have 12.5. Remember, I'm setting the rate equation for experiment number 1 over the rate equation for experiment number 2. Okay, so experiment number 1, my rate is equal to 12.5 times 10 to the negative 6th. I'm going to put the units in here just because I can right now, equals K, and my concentration here was 0.080 X and then 0.040 Y. Okay, that's experiment number 1. I'm going to take that and divide it by experiment number 2. Okay, so I'm going to have 6.25 times 10 to the negative 6th moles over liters times seconds. Then I'm going to have K, that's going to allow me to cross that right off, 0.040 X, 0.040 Y. So that's going to allow me to cross that right off. Okay, it makes the math a lot easier. So now what I got to do is divide these numbers out. So 12.5 times 10 to the negative 6 divided by 6.25 times 10 to the negative 6 is going to be 0.08 divided by 0.04 is going to be 2.0 X. X is equal to 1. So for iodide, it's going to be first order. That's what we would plug back into the reaction. All right, so now for the other ion, because I'm blanking on what that one's called right now, I'm going to go ahead and pick experiment number 1 and experiment number 3. Okay, because the iodide is kept constant and then our other molecule concentration changes. So if I do experiment number 1, and you may get to the point where the math kind of becomes automatic. You can kind of see it. If you're there, awesome. And the rest of you, don't worry about it. Okay, we're just learning about it. So 12.5 times 10 to the negative 6th moles over liters times seconds. We've got K, and I'm going to go ahead and plug in 0.080. I'm going to go ahead and put the 1 here. This one works out, meaning that you have two experiments that make it easy to calculate rather. Every once in a while that's not going to be the case, and you're going to have to actually plug this number in order to solve for y. But in the beginning we try to set you up for success here. So 6.25 times 10 to the negative sixth moles over liters times seconds. Those are all going to cancel out right there. We're looking for K, so that's going to be gone. We're looking for 0.080, so that's going to be gone. And then we've got 0.020y. Oops. All right. And so we're solving for the y here. Now if we divide these two numbers again, we get 2.0 is equal to 2.0 to the y. Remember, you're going to use logs. Most of the time we're going to see first or second order if we determine it this way, so it's not going to make the math too bad. So y is going to be equal to 1. So we also are going to have first order for our other ion. So O8 2 minus, it's also first order. So the answer to the first part, the rate is going to be equal to K, first order, and now you will see some sources that do not write the 1. I do. It just reminds me that it's kinetics and it's first order, but it's also implied if you don't put it that way. All right, now part 2, what we have to do is go back and use some of our data and plug in and solve for K values. Now, I'm going to show you how to do the first one. Change colors here again. And all I do is go back and take that data. So for experiment number 1, my rate was 12.5 times 10 to the negative 6, and I'm going to put the units on here. Remember, this whole thing is second order overall. Where did I get that from? The 1 plus 1 gives me second order overall. So if we're thinking about units, okay, you can always go back to number 19, but I'll show you how we determine what those units are. Moles over liters times seconds. We're solving for K. I've got 0.080 moles per liter. I'm just going to go ahead and cross those off right there. Okay, that's going to get rid of one set. But then I have 0.040 moles per liter. Okay, I plug and chug, solve for K, multiply these two numbers, take 12.5 times 10 to the negative 6, divided by it. I've still got 1 mole in 1 liter that did not get canceled out. So my value for K here is 3.9 times 10 to the negative third. And my unit is liters over moles times seconds. So like we said, it's second order. So the exponent on liter in moles is 1 less. So it's first. And if you do the rest of the other experiments 2, 3, 4, 5, give you the exact same number. So our average K, and it's always a good idea to solve for all of them just to make sure, but I'm not going to just redo that over and over again, is still going to be 3.9 times 10 to the negative third liters over moles times seconds. Okay, I hope that helps. Good luck, and let me know if you have questions.